Hey, welcome back to Data Structural Algorithms. Today we are going to discuss about binary search tree delete. So there are three cases to understand to delete a node from a binary search tree. The case one is deleting a node which is a leaf node. Okay. The second case, deleting a node which has left or right child. The third case, deleting a node which has two children. Okay. Um, so these three cases, like tackling these three cases is really important, and deleting node, it's going to change the structure of the binary search tree, so we need to maintain intact right after the deletion. So if we are addressing these three cases, then we are done. Deleting a node from a binary search tree is really an easy job. So taking a theoretical understanding, how are we going to delete it? Okay, and with our uh, uh, conceptual understanding, right? That's more important before we move on to coding part. Suppose we are going to delete a node which is 3. Here 3 is going to be leaf node, that is nothing but in the case 1. Deleting the node 3 is very simple. It's not going to alter any, it's not going to change the state of the binary search tree. We just go ahead and delete it and make the pointer to null, which was pointing to the node 3. So the second case is deleting a node which has children, which has either a left or right children. In this case, 66 we are going to delete, which has a right children. So how are you going to do that? So what we need to do is, like, we need to make a parent to the parent of 66 to point to 70. So what we need to do is just remove that guy and move this guy to children of 70, move the 70 to children of 15, and free up the 66. This is also simple. After deleting node 66, the binary search tree state is not changed. That's the So whenever you delete, we should make sure that the state is not changed. Suppose the third case is deleting a node 30 which has two children, 25 two children. Each children is another subtree. In fact, here in that case, like, it's pretty different, but it's not tough. Of course, it's really very easy. uh, we need to find the smallest element of the node 30. Okay, not from its left side, but it should be from the right side. Suppose the smallest element of the right subtree of 30 is 40. Understand clearly, the smallest element of 30 in its right subtree, that is 40. You just take the value 40 and assign the value to the element which we are going to delete, which has two children. Okay, then initiate a request to delete a node 40 from its right subtree. Okay, not start with the root node itself, like issue the delete request to its right subtree, and the value which you wanted to delete is 40. In that case, 40 is the target guy to delete. Okay, that is the children of 50. uh, if you see, the 40 is leaf node, right? Like, deleting a leaf node is very simple. So it will fall back to a place where it may be a leaf node or it may be a node which has a single children. So deleting these two use cases is really simple. So that's where we come in. Deleting a node 40 is really simple. You just delete it. As simple as that, right? So after that, if you check, the state of the binary search tree is not changed. So let's see the performance. It's the order of log n. It's really great to delete an element. Let's move on to uh, coding part. So let's keep this guy here because it's going to help us to write code. So we are going to continue with the code which we have seen in the last session, that is insert. So now we are going to write delete here. Okay, so delete It's going to take the tree in which we need to delete it. So node star root node, we are going to take it, and the value which we need to delete. Okay, that's great. So first we need to check the root element is null or not, right? If it is not null, then only we can delete it, because if there is no element, there is no point of deleting the node, right? So check root is there. Okay, if root is there, then only we. So we need to first traverse the node which we are deleting. So we need to just keep on moving left or right based on the binary search tree properties. So first is value is bigger than the value of root. Yeah, in that case, okay, move the pointer to the right of the child. Okay, root dot right equal to delete of root of right and the value which we need to delete it. Okay, else if value is less than root of value. Okay, in this case we need to move the pointer to left. Okay, root of change we have missed here. Okay, so these two guys will help us to take to the node which we are going to delete. When this condition comes into picture, okay, value equal to root dot value. When this guy come in, like this guy will not come, these two guys, like the first and second if condition will help us to reach the point where we see the value and the root value is equal. Okay, so now it's important to understand the three cases. First we need to check whether um, the node which we need to delete as left child and right child. Okay, if both are there, it's a different use case to think about it. Let's come back to that little later. Now we need to think if root as left. Okay, in that case, okay, root as left, think about that, we need to delete. So we need to, before that we need to take the backup of this guy. So node to node to delete. Root is the node which we are going to delete. So what we are going to take, what we are going to do is the node which we are going to delete, if it has a left child, we are going to assign the left sub to the root. Root equal to root dot left. If it doesn't have left child, then we are going to assign right. Okay, sorry, GHT RGHT to the root. Okay, and then we need to free up this guy, node to delete. Okay, make a node. So now suppose if it has children both, so we need to find out the minimum element of its right subtree, right? So node, we need min node, and then we need to write another function, find min node, which is nothing but find a min node, a right subtree in right subtree. So we need to pass the right subtree pointer. So it's going to bring in, let's move to find min node function, and the node is, we are passing the root, the tree base pointer, in which we need to find the minimum. We need to check if the root, of course the minimum element is going to be in the left of the tree, not the right of the tree. So we are going to check left, the element has left children or not. Okay, if it has, then it's a time to go again check is there any another left child or not. So that's where the recursive function comes into play. root dot left. Okay, and when it reaches, think about it, reaches 3, and then we are checking root dot left equal 3, then this null, then it comes. Okay, we return the root element, which is the minimum element. Okay, that's great. So we know how to find minimum node. Okay, we got that. Now we need to change assign the value of the root, assign the value of the min node to root value, and then okay, raise a request to delete the node in the right subtree. Go to delete. Okay, what we need to do, root dot write comma, the value should be min node value. Okay, it's done. So now we need to return root. Okay, return the root. So let's run and see the program working or not. First we need to delete node 3. Okay, how does it work? Something is missing, error, left delete node, semicolon is missing. Okay, no error. Okay, we have deleted node 3, so we could not find node 3 yet. So if you check 30, 25, 5, 3 is no more there, then 27, 50, remaining same. Yeah, that's great. Okay, let's delete a node which has children, single children. Okay, instead of this, let's delete 5 and print that 3, then delete delete 30. Okay, let's see. Okay, so we deleted 30. We deleted 30, it worked. I deleted 5 as well, it worked. When you delete 5, it becomes 30, 25, 3, 30, 25, 3, then 27, 50, 40, 27, 50, 40, 66, as simple as that. Yeah, that's it. Thanks for watching.